tell me this square root of 4 minus x squared is going to turn into?
4 cosine theta.
Not quite 4 cosine theta.
2 cosine.
A cosine theta, so 2 cosine theta. This will be 2 cosine theta. The root part will be. What would the root part here be? What would that root part turn into here? Root 3 cosine theta. Okay? Every single time. If you make that substitution, then the radical part simplifies very nicely, doesn't it? Okay. Now, yes?
If we are assuming 4 is A, and it's...
No, 4 is A squared. 4 is A squared.
We're always using sine as our initial substitution?
Yes and no. Yes, if you see A squared minus x squared. Stay tuned. What if we see A squared plus x squared instead of A squared minus x squared? We do a different substitution. Instead of replacing x with A sine theta, we use A tangent theta. And the reason why is because of the algebra in there. When you take this and plug it in here and square things, you're going to need to you'll use this identity instead of the one that took you from sines to cosines. And then there's one last one, and that is, what if we see x squared minus a squared? So not a squared minus x squared, switch it around. Then we're going to do this trig sub, a secant theta. Now I'm going to take you through examples of each of these. Did you have a question?
Yeah, I was going to ask, so basically the problem that we look at, if it is a difference of squares, then we use sine substitution, and if it's a sum of squares, then we use the tangent substitution, and if it's like a backwards difference of squares, like as you see there where it's x squared minus a squared, so it's basically like difference of squares except off by -1, we would use secant.
I'll agree with your middle statement, which was that if you see a sum of squares, you do a tangent substitution. But a squared minus x squared and x squared minus a squared are both difference of squares. There's not really one way to distinguish one from the other than which is the variable, which is the constant. So, yeah.
Okay.
Yeah. Okay, so are you ready to do an example? Let's do that one right there. A trigonometric substitution problem, in my opinion, is a type of problem that you can kill like 6 birds with 1 stone. So like on a test, I can ask one trig sub problem like this, and it will test pretty much the whole thing. And when we get to the next topic after this one, partial fraction decomposition, that I can give you one of those, and it will basically cover everything we've done. Like it'll have within the problem every single type of technique that we've had to use. So this is where it all starts to this is the end. I mean, we're almost at the end of integration here. Okay, what are your, I'm going to go refill this with water. I just want you all to think about that. Okay, and I'll be back and we'll see if anyone has an opinion. It's going to take me 30 seconds. See if anyone has an opinion as to an approach. Yes.
So are we could be allowed to use our formula sheet on the test just because it has like already.
What are you referring to?
If he sees this, can he just replace it with this?
Yeah.
That's what he's asking.
Yes. You can use the formula if it's on this one sheet right here. The problem is that won't work for that one.
Yeah.
Yes, but yes, you can. Yeah, so on a test, you're not going to see any of those just in their formula forms. There will be some tweaking to it like this where you can't use a formula right off the bat because of the x cubed. Yes?
Integration by parts. And then just use this.
Maybe?
So could we?
Yeah? Integrating, oh, okay, I see what you're saying. Are you sure your voodoo will work on that?
Well, I figure if we have x cubed in the top left and the rest of it in the bottom right, then our x cubed would just become somewhere with x power right, and then we'd just be doing an integral of that, which is what we just learned. And that will just give us x's, different powers and fractions when we finish. And then when we multiply back out, it's just going to be just power rules all the way across.
When you integrate this, though, you're saying that would be your dv in integration by parts? So when you integrate that,
It's this, right?
right? Yeah?
And
But
this is all just, powers of u with constants, right?
well, you got natural logs in there. All of that's going to be multiplied by. Look, in integration by parts, let me just. This would be x cubed. This would be 3x squared. This would be square root of 16 minus x squared. And then this piece is your formula.
Yeah.
That formula times x squared. And you got ln's in there. It's going to be nasty, so I'm not sure I would go that route.
How come the integral of square root of 16 minus x squared isn't for cosine theta?
Well, I haven't. No, we're not doing. There was talk of doing this by integration by parts, not trig sub.
Oh, I'm sorry.
Yeah. So any other sorts of attacks on this, or did y'all just want to go straight to trig sub? Straight to trig sub. Let me show you what my instinct is on this. My instinct is to do this. It may not work, but my instinct on this one is to do this. That's my instinct right there. So why would I do that?
Sine theta for the x squared, so just do your sine theta.
Yeah, but I'm not even thinking trig sub. I'm not even thinking of trig sub. I'm thinking of u sub. What would my u be here? How about 16 minus x squared? Right? What's the derivative of that? Negative 2x dx. Do I have this? Well, kind of, right? Off by a constant. So negative 1/2 du equals x dx. Y'all there? Okay, how can I rewrite this integral? This integral will become, what's x squared? Ah, well here, I can get x squared from this, can't I? Wouldn't that be x squared is 16 minus u? So that first x squared is 16 minus u. And then what's the square root of this thing? That's the square root of u, isn't it? So square root of u, I'm just going to write that as u to the half. And then what's x dx? Negative 1/2 du. Is that doable? Yeah. I can just pass this through, pass that through, and I'm done. Well, I have to integrate still, but yes. So I guess the point I'm making here is that we don't want to get too much tunnel vision. When you're working a problem within a section, of course you want to think that it's going to use the method that they're trying to get you to learn. But this is what makes the integration difficult, especially your next test, is that you're not going to have anything prompting you as to what technique to use. So if you use basic U substitution here, yeah, you're going to be there. Look, that was pretty quick, right? We're not done, but right? That wasn't too terrible. I think I'm just distributing that through. And now I could integrate each of those. Sorry, this is still an integral here. Okay, so I could handle that. Now, let's act like we weren't thinking this way, and let's try it with trig sub. And we'll see which one takes longer and is harder, right? Do y'all agree we're here? Like with this method, we're done. We could keep going. Okay. So now, if we're thinking trig sub, I hope that everybody sees that we have this form right here. Right? That's the form we have. So we need to make a substitution that x is going to be replaced with what? In this case, 4 sine theta, right? 4 sine theta. If we make that substitution, I know automatically that 16 minus x squared will turn into what? 4 cosine theta. And there's one more thing that I have to do, and that is figure out what I'm going to replace dx with. So I'm going to replace that, right, with 4 cosine theta. X cubed, I'm going to have to replace that somehow, but how can I replace that? Well, if that's x, what's x cubed? It's just both of those cubed, right? Both sides cubed. Yes? I'm going to show this one time, okay? Because I've shown it, but in more detail, okay, this time. But this is the only other time I'm going to show it, okay? Square root, I don't mean that. That sounded like I was getting mad at you. I just want to make sure everyone understands I'm going to show this one time. Okay, 16 minus what's x? 4 sine theta, right? 4 sine theta, but then I'm going to do what with that? Square it, right? Boom. Okay, that's square root of 16 minus what? 16 sine squared theta. What do both of these have in them? 16. Factor it out, I'm left with 1 minus sine squared theta. What is 1 minus sine squared theta? Cosine squared theta. Okay, take the square root of both of those. What do you get? 4 cosine theta. Okay? So, imagine that this would have been an A, right? Imagine that was A. Then this would have been A, right? And that would have been A squared. And this would have been A squared. Factor out an A squared, comes out, you take the square root of A squared. This will always be A, and this will always be cosine theta. It will always be cosine theta because this is going to turn into 1 minus sine squared theta. Okay? Every time. But we don't want to have to do this work every single time. I know some instructors make their students actually write this down every single time. I just want you to, it's supposed to be a shortcut. It's supposed to make it go faster. So, all right, so we know we can replace x with this. We can replace that root junk thing with that. And then I'm going to take derivative of this. What's the derivative of that? 4 cosine theta. Careful here. 4 cosine theta d theta. Now look, I realize these are the same, okay? In this particular problem, these are the same, except this one has a d theta, that one doesn't, okay? All right, if I rewrite the problem, this integral becomes x cubed. What's x cubed? 4 times 4 times 4, right? 64. Sine cubed theta times, okay, what's this piece? 4 cosine theta. And then what's this piece? 4 cosine theta d theta. Did everyone see where all those pieces came from? So now this is going to become 4 to the 5th integral sine cubed theta cosine squared theta d theta. So what I did is I got tired of writing 4 times 4 times 4. This was 4 cubed, right? Times 4 times 4 again, that's 4 to the 5th power. I just brought that out front.
I'm so sorry. How did you get 2 4 cosine theta d theta? Like, how did you get 2 of those?
How did I get?
2 4 cosine theta.
Okay. Do you know where x cubed came from?
Yes.
Okay. What did we say this would be?
4 cosine theta.
Okay. What's dx? right? That. How do we do that? So should I pull a stick? I should pull a stick. Okay, so let's see how this goes. Nobody say anything. Okay. Mohammed?
I was having my name. Okay. So.
So do you know how to do this one? It's okay if you don't, but do you know the next step for this one?
No.
Okay. Tatum? Do you know the next step for this one? No? It's okay. Chris? Chris Ochoa?
Right here.
Do you know the next step for this one?
Yeah. So what you want to do is peel off the sign.
A single factor of sine. Okay.
Factor.
Single factor of sine. And if you did that, you'd be left with a sine squared there, which you're going to do what with?
Let it be u.
Not quite, because you pulled a sine out, right?
Okay,
Sine's going to be here.
Yeah, you let cosine be u.
U's going to be cosine, so that's going to be u squared, but then that's sine squared, so you have to get rid of the sine squared
By using the.
Pythagorean identity. Okay. Did you have that written down? Were you cheating?
No.
Where's that coming from?
We did that.
Previous section. Okay, that's what I'm talking about. You have to understand the previous section, or else you're dead in the water. I'm not saying you are Tatum, but that's the way you need to know it. That's the way you need to see that now today, not a week from today. Okay? All right, that's the way it goes. So from here, 4 to the 5th stays out. Integral, we're going to rewrite this as sine squared theta, cosine squared theta, peel off a sine theta, d theta, and now we make a basic u substitute. Oh, no, wait, hold on. We want the sine squared switched. Sorry. I'm running out of room. I think this way is a little bit harder than the way that I did it initially, right? We're going to get to the same result. Okay, equals 4 to the 5th integral 1 minus cosine squared theta times cosine squared theta, sine theta d theta, and now our u substitution. U is cosine theta. du is negative sine theta d theta. Negative du is sine theta d theta. Just getting my negative to the other side. And now I rewrite the whole integral. Negative 4 to the 5th integral 1 minus u squared times u squared du. So replacing all my cosines with u, my sine theta d theta with negative du, pop the negative to the outside, distribute. U squared minus u to the 4th plus c. Yeah, I don't know what I'm doing. You know what I'm doing? I'm thinking right now. I'm thinking about something. I'm sorry. Distracting myself up here. Pardon?
You should think about adding an integral sign.
I should probably do an integral sign and a du at the end, right? I was thinking about when I was in Cal 2. I'm trying to remember, like, when I was in Cal 2, like, could I see that, like, from here to here? Was I at that point at the right time? I don't remember if I was. But I'm just telling you where you need to be. Like, that's hopefully you can be there. All right, antiderivative time. So, negative 4 raised to the 5th times 1/3 u cubed. We'll just do it all like this. Keep that outside. And then we have minus 1/5 u to the 5th, and then plus c. What's u? U is cosine theta, right?
You just want to see leave 4 to the 5th by itself.
What is 4 to the 5th? Someone do that yet? What is it, 264? Should be a power of 2. Hold on. Is it,
Negative 1,024.
I was going to say, is it 1020, 1024?
Yeah,
Yeah.
negative.
Okay, so this is negative 1024. So I'll distribute that through. Negative 1024 over 3 cosine cube theta plus 1024 over 5 cosine to the 5th theta plus c. Not done. Why are we not done?
You can put it back to the way it was.
Yeah, we got to get it back to in terms of x. It's in terms of theta right now. So negative 1024 over 3. What is cosine theta? So where am I going to get that from? Cosine theta. Well, what was the trig substitution we made? What was the original trig substitution we made? We replaced x with 4 sine theta, right? Right? So from here, x over 4 is sine theta, right? And I can draw a triangle from this. Right? Opposite over adjacent. Opposite over, what the? Opposite over hypotenuse. I don't know why I said that. Okay, and then can you solve for this side? Square root of 16 minus, it's appeared, hasn't it? That has appeared. It should always appear. All right, now, do you know what cosine theta is now? Yes. So this is going to be the square root of 16 minus x squared over 4, that cubed, plus 1024 over 5, then square root of 16 minus x squared over 4 to the 5th power, plus our constant.
It's like salt in the wound. Right?
There we go.
And you do all that math, and then it's like, oh yeah, but plus c.
Yeah.
Screw you, integrals.
I like the other way better, the shorter way, but it doesn't always, you don't always have a shorter way.
If we do all this when it was possible to do a U setup, would
Uh-huh.
you give us extra points?
Extra points? I don't know about extra points.
Would you give us like 10 extra points to do all this?
That'd be dope.
Yeah. I mean, I don't know. I went off, when I put the problem up there, I just went off of what my instinct was. It worked. It won't always work. All right.
Sometimes the professor would give points for the quickest, shortest code.
Professor?
Yes.
Is it fine to just leave it like that, like draw?
Yeah, I mean, that's it right there. We're not going to do anything with that.
Sir, I got a question for you. So like the final answer, how did you formulate that? Like I get where all the variables came from, but like what structure did you take that from originally?
Like this?
The whole thing, like the bottom.
Well, this is cosine cubed, right? Cosine came off our
You want to put it
triangle.
back in terms of x.
Yeah, we just had to get them back in terms of x, exactly. Okay, let's take a look at one last example. Should wrap up class with this one. I think it's safe to say you're going to need to do a lot of practice on this. It's my feeling that this section, trigonometric substitution, is the section where you really start to feel like this class, like the intensity of this class is this section. There's just so much involved in these problems. So be ready for that. If you can handle this, I think it's a really good sign. Yes?
This class is really going to make you feel like you're camping because it's so intense. You're cool.
I do.
My dad would appreciate that. My uncle even more. All right. What's that? Maybe a U sub on this one? God, I don't know. Maybe it does go by U sub.
It's the same as the last one where we have a hidden x squared, open x squared.
Yeah, so maybe it will. Well, let me just hold on. Don't go too far. I don't want this to go with U sub. I want to force us. So let's just change that to x to the 4th. Now your U sub's pretty much dead because you can peel off an x, but you're left with an x cubed. And then you can't do anything with that x cubed. Okay. All right, so first couple of things we have hidden within this problem. We have a square root, just like the form that we were looking at. So let's just rewrite this as x to the 4th over the square root of 4x squared plus 9, all of that cubed dx. Right? All right, so does that fall into one of the forms that we have? So here are the forms. We've only worked with one of them. The one that we've worked with is this one. The other one that we have is this one. And then the last one we have is this one. We've only done one example, right, of this. That's all we've done. So this one, does it look like this one, right? Because it has plus in between? It does, right? Now, it doesn't matter if we switch these. X squared plus a squared is the same as a squared plus x squared. But we have a 4 in front of the x squared, don't we? And we don't in this formula. So what I'm going to do next, I'm going to take it out. So I'm going to take it out. I'm going to take it out of the root. I'm going to factor 4 out of here, right? If I factor 4 from here, I have to factor 4 from here, from both, right? And then 4 is going to come out of the root as a 2. And then it's going to get cubed and become an 8, and it's going to come out of the integral completely. Say that again. 4 comes out of both of these, comes out of the root as a 2, gets cubed, and then comes out of the integral as a 1/8.
Good grief.
Okay, square root of x squared plus 9/4 cubed dx. Everyone understand the 9/4, right? Factoring a 4 out of 9 becomes 9/4. All right, now does it look like this? Yes? What's a for us? 3/2, because a squared is 9/4, right? So a for us is 3/2. Now, what is the trig substitution we make when we're using this? And I only showed it to you one time. It was x is equal to, let me just bring it back up so you can see it. Right there. X is equal to a tan theta, okay? So x is equal to a tan theta. And then what's this big square root thing going to turn into? That we don't have to show all this work, but what does it turn into? A secant theta. And then we'll be able to take the derivative, so we won't really need to worry about that part. So, okay. So working with this, here comes the trigonometric substitution. x is replaced with a, which we said is what? 3 over 2 tangent theta. The square root of x squared plus 9/4 we know is going to turn into a 3/2 secant theta. And then what about dx? Dx, I just calculate it. What's the derivative of this? 3 over 2 secant squared theta d theta. Okay, so for every trig sub you ever do, you're going to need to know what's the trig sub, what does the ugly root turn into, and what does the dx turn into. You're always going to need these three pieces. And now we get to rewrite it. Here we go. Rewrite time. All right, I'm going to keep that separate there. Okay, so here's where we are. We're going to go 1/8 integral. All right, what about the top here? X to the 4th. It's this thing to the 4th power, right? So I'm going to write 3/2 to the 4th tangent to the 4th theta. That's on top. Questions on that? Over. Now be real careful here. This thing right here is being cubed, isn't it? The root part gets replaced with what? 3/2 secant theta, but then cube it. So 3/2 cubed times secant theta cubed, right? Secant cubed theta. So all we did was took this root and cubed it, which meant cube that, cube that. We done? Questions? Am I done? What else do I need to put in that integral? dx. Don't forget dx. Everyone always forgets dx. This poor little guy right here. What's dx replaced with? 3/2 secant squared theta. D theta.
Where does secant cubed theta come from?
That's the root down here, right? Being cubed. And the root is this, so we cube this and this. All right. Shall we proceed? We've got 5 minutes. So we're not finishing this problem. I think that's obvious, but we'll at least get, hopefully, a point where it's set up. Lots of things start canceling out here, don't they? So integral, let's see. Let's do, I'll leave some room. 1/8. Okay, how about these 3/2? Yeah, like all of these are gone. We leave one here, right? And then that one and that one together. 9/4 can come out. 9/4 comes out, so I'll just put 9/4 here. Integral. And then we get some secants to cancel there. Right? 2 of those cancel, so I have 1 secant on the bottom. I've got a tangent to the 4th on top. And I've got a secant on the bottom. Right? Now, we haven't dealt with anything like that before, where we've got that sort of tangent and secant together in a ratio. We've had them like side by side, haven't we? But not like that. So whenever you see this, I would just get everything in terms of sine and cosine. Okay, so what does a secant on the bottom really mean? Cosine on the top, right? So this is really 9 over 32 integral. We have sine to the 4th theta over cosine to the 4th theta times cosine theta d theta. So tangent to the 4th is this. Secant on the bottom is a cosine on the top. And then one of the cosines cancel, right? So 9 over 32 integral sine to the 4th theta over cosine cubed theta d theta. And that looks disastrous, actually. Yeah, no, I mean, would you all agree we've taken a complicated integral and got it to a trig integral now? At least that we've got, right? So I think this is probably a good stopping point. I only have 2 or 3 minutes. We'll come back, we'll revisit this. What I would do in terms of homework is make sure you get through all the stuff for the first half of this section 6.2. So that means everything up through like number 36. So 1 through 36, all those problems should be fair game now. And then numbers 39, 40, 41, those problems are where the trig sub starts. And then there's a bunch of problems on trig sub. Okay. We will spend a lot of next class doing more of this. All right, because on our schedule, we're supposed to finish this section up this week. So 6.2, we're supposed to finish on Wednesday. So I want to spend at least the first half of class doing more of this. And then we might jump into the next section, which is partial fractions on Wednesday. Yeah, let me turn off the camera.